Right, so this is going to be a new module for us after Python. Today we will talk about high performance computing cluster, particularly the cluster that we have at IIT Mandi. So this is the plan for the lecture. We will start with an introduction, and then we will talk a bit about virtual environments, how to set them up on the cluster, and then we will well, since we are only used to using Python till now, so I will be using Python as a compute exercise to run, because we have to run something for computations on the cluster. So we will be using Python for computations. I will be telling you how to use scripts on the cluster. They are called PBS scripts, and then we will also discuss a bit about automation, because we are doing all this to ensure that our time is also used efficiently. So for that we will have to learn a bit about automation, mainly about the ideas of automation, what level of automation is possible that will help you save time, actually a lot of time, so that you can spend that on more interesting things once your computations start running. We will do a hands-on, and I will also give you a couple of exercises, one to practice in the class and one particularly to take home and practice later. So let us talk about some introduction first as to what is an HPC, what is an HPC cluster, how does it look. I have not put pictures here because I actually want to take you to the cluster room if they allow us, because these are secure facilities, but hopefully we will be allowed to go and have a look at least from the outside. Okay, so I've just put a nice diagram here just to give you an explanation of what an HPC cluster looks like. So here's a topology in the figure as to what a cluster is. So a cluster is as the name suggests, it's a collection of computers. It's a cluster. Okay, it's a collection of computers connected to each other in a certain way. So topology, as you know, loosely speaking, it's basically how things are connected to each other. So this is a figure as to how our cluster topology looks like. There are different kinds of topologies available, but we'll not go into details of what topologies are, but what our cluster looks like. So we have a head node. This is the terminology that you will hear when you start using clusters. So head node is, as the name says, it's a head, right? So you will connect to the cluster through a head node. So sometimes it's also called a login node. So user logs in, and to log in, you have to use the institute intranet. So you should be in the institute connected to a LAN or some sort of an institute Wi-Fi. Only then you can connect to the head node. From the outside, if you are using your mobile phone network or some outside network, you cannot connect to the cluster for security reasons. So you log into the head node, and typically your IP address will look like 10.8. something. That's the institute IP address that you typically have. Then once you log in, this head node is connected to a switch. Switch is like you have a switch where in your hostels and so on. So these the job of a switch is to enable communication between different computers. So there's a LAN cable, literally a LAN cable, that connects a head node to the switch, and the switch has lots of ports available for LAN cables, and these LAN cables connect to different other computers, and the other computers are called compute nodes. So there is one head node in the cluster, and there are a lot of compute nodes. I think 160 plus compute nodes is what we have. So the numbering at IIT Mandi is looks like N1, N2 all the way to N100, N150 and 160. Okay, so this is how you address compute nodes. Your compute job was sent to N31, for example. Right, so this is about a topology looks like. So N1, to communicate with any other computer, it has to go through a switch. Now to connect to a switch, it has actually two cables. One is a standard 1 Gbps Ethernet cable that you have in your computers connected here. It's called RJ45, I think that's what it's called. And the other is actually a faster one called 10 Gbps. Okay, so that's a different technology. That's much faster. So I think that's optic fiber based, and there are actually faster switches available, but we don't have that in the HPC cluster at IIT Mandi. So the fastest communication that can happen between a node and a switch is 10 Gbps, and of course if you try to send lots of data, then the speed slows down. Right, so the compute node will communicate to the head node through the switch, and vice versa. And also compute nodes can talk to each other if required. Usually that's not required, but if required they can also talk via the switch. Now since the switch is only working for the cluster, this particular switch, so this switch will give some sort of a local IP to the cluster. So you don't need to worry about that, but every node or every computer or every blade or every I mean the different terms used, typically we'll call it a node. One physical machine like we have here will be called a node. So every node will have its own IP address, okay, inside the cluster, and then outside the cluster, and the whole head node has one IP address, which is how you access the HPC cluster. So to connect to the institute network, only the head node is connected, no other node is connected, right. So head node is typically used for login, for scheduling jobs, because many people will want to send their jobs. So head node has a scheduler installed, a PBS torque, that we'll talk a bit more about that in a while. So that the job of a scheduler is to schedule jobs. So whoever sends the job first, who has a priority, who is paying more money, etc., etc. So based on these things, it will schedule jobs. It's not for computation. In fact, the configuration head node has is actually not as amazing as the compute nodes, and that makes sense because you don't want to run computation expensive jobs on the head node. So you should not be running any computation on the head node. You should always use the scheduler so that your job gets sent to a bigger and a faster machine, which is a compute node. And as the name suggests, compute nodes are used for computation, suited for heavy computation. Typically our compute nodes, we have a heterogeneous cluster in the sense that compute nodes have different configuration, because some of them were bought 10 years ago, some of them were bought very recently, so the configuration differs. So it's a heterogeneous cluster. So typically they'll have 2 processors per node. So they are different from a standard desktop machine. So the motherboard has 2 processors, and each processor has up to 12 cores in it. Now these words will start making sense when we talk about parallelization starting 2 weeks from now, but you have some idea of what is the meaning of 12 cores. For example, your laptop may be octa-core processor, so it has 8 cores in it. Okay, so 12 plus 12, 24 cores in one node, so to say. The RAM would be north of 64 gigabytes or more, so depending on what configuration we have, and typically it will have 2 terabytes of local storage. So whenever you run a computation, the data that gets generated will be stored on the compute node, because there is no point communicating the data every time to the head node, right. So to make things faster, because as we learn soon, sometimes the data transfer becomes the bottleneck. It's not the computation but the data transfer. So one has to be smart enough to understand those things as well. So this is how the topology of the cluster looks like. So typically these compute nodes are in a rack. We don't have one here, but usually they'll be like an almirah, and there'll be lots of compute nodes. They just slide into the rack. On the top it has a switch to connect the cables from the nodes from the compute nodes to the switch, and then on the side we have some power strips where you can connect because these are power hungry machines. And as I said that we'll have one optional lecture on clusters or data centers, as they are typically called nowadays, although data center is also used for computation, not just for storing data, but they are called data centers. So data center, we'll have a lecture on that where we'll talk about the different aspects of managing a data center or setting up a data center. And these are very important things nowadays, because data is everywhere. Even startups are starting to sometimes set up their own data centers if they cannot use the cloud, but many cloud services are now available. So they are huge data centers. So there are different scales. Our cluster is less than the size of this room, but you will have Google, Amazon, Microsoft. They'll have data centers which are of much bigger than probably our campus. So this is the kind of scales we are looking at. So we'll have one lecture on data center. We'll learn about different aspects on how to manage these centers and how to set them up. So let's do a website tour, and through this website tour I'll talk about different aspects. So let's click this. So the website URL is research.iitmandi.ac.in/HPC. It's also available on Insight On the left hand side, there is a link available. Right. So, if you click, there is no dark mode, light mode, and that is the only color we have. Hopefully, you can see the website. You do not need to read anything as such. You can open it on your machines if you want. So, there is an about us page where it talks about just some basic ideas. So, what's important here is, and you should, if you plan to use the cluster, you should definitely read this website, all the pages in detail. Okay, they are very useful. In fact, if you plan to use any cluster or cloud facility, it's worth reading their manual first. Right. So, it has two subclusters. One is called CPU HPC, the other is called GPU HPC. CPU HPC, as the name suggests, is for CPU based parallelized jobs, and nowadays we also have a lot of GPU based parallelized jobs, particularly machine learning applications. So, we also have a GPU cluster if you plan to use GPUs rather than CPUs. So, for GPUs I will not discuss much now, because GPU discussion will happen towards the end of the course, where we talk about some GPU based parallelization and so on. Okay, so, for now our parallelization, the word parallelization for us will typically refer to CPU based parallelism. Right. So, the IP address is 10.8.1.19 for CPU HPC, and for GPU HPC it is 10.8.1.20. So, you will use these for logging into the cluster. So, it talks about how to create a new account. I am sure everybody has got an account or has applied for one by now. It has some deletion policy. Then there is a page on software. So, let us click that. So, it talks about the compilers available. We will discuss more about that when we start talking about Fortran. Then it has some environments available that you can use to access some for example, CUDA libraries, MPI and so on. MATLAB is also installed, and then we have some other packages available such as Sage, GROMACS, Singularity. Singularity is particularly very useful because it allows you to use anything, any software on the HPC cluster. So, you can literally set up an environment on your local machine like a virtual machine, but much faster, and you can play around with that. You can test it for smaller problems, and then you can just copy that onto the cluster. So, you do not have to request for any installation of any software on the cluster. So, we will talk more about it. So, this is an introductory lecture on HPC. So, you will start learn how to use it, what it is, and then in the future we will keep using it for running some compute hungry jobs. So, there is a tab on submitting jobs here. So, this talks about how to submit jobs. So, I will take you through this in more detail when we actually start doing this in the demo. Because once you are ready with a job, once you are ready with a script and an executable, you have to submit it so that it can start running on the compute node. Okay, some scripts are available here. So, you can just, because you won't start with scratch. In fact, we won't start with scratch in this lecture. So, we will just copy one of these scripts which is closest to the one we want, and then we will start modifying them. We will incrementally, so that we are able to achieve whatever we want through our exercise. There is a page on list of queues. So, queues are provided because different people have different requirements and different people have different privileges. So, for example, just as an example, you can see that there is a queue called day. So, this is for running jobs which will run within a day, and then there is a queue. So, the time available is 24 hours. So, 24 hours 0 minutes. So, that means that after 24 hours your job will be killed. So, that it will automatically it will be cancelled. So, that is the maximum you have. So, if you think that it will take more than a day, then you should typically send to a week queue, which is 168 hours, which is 1 week. Similarly, there are some priv queues which are private queues. So, people, faculty members have written projects, sponsored projects, and they have got some money to buy some compute nodes. So, what we do is what HPC does is that they will take the nodes from them and then they will put them in the cluster, but they will manage it. Software management, hardware management will be done by the HPC people at IIT Mandi, but the people who have contributed, they have sort of prime access to these compute nodes. But when they are not using it, then anybody else can use it. So this allows for the maximum usage of these facilities. So there's a queue called low PR, that's low priority. So when nothing is working, everything is full, then you can use low priority. So what happens is in low PR, your job goes to one of the private queues if they are available. But as soon as those who are actually, those who bought those computers, if they send a job, your job will be killed. So what we typically do is we create checkpoints. So whenever, so for example, let's say I'm running a simulation and it's a transient simulation of something happening inside, some balls being thrown in the room. So I keep doing simulation and I keep generating some time snapshot of the state space of all the balls at different times. And if my job gets killed, then I can start from wherever the last checkpoint was. So that helps us save time. So I can use low PR queue for running jobs, and then without worrying about the fact that if it gets killed, all my data gets lost. Okay. And there's other queues as well, so you learn more about it if you read this page. So this is the idea of, so you have to decide on which queue you want to use when you are sending a job for execution. Contributed nodes. So this has some contribution, this has some discussion how if a faculty member wants to contribute a node, what are the policies and so on. Okay. Then there is a page on quick start to job submission, which is again a very useful page that you must read. I'll not, these are very basic, so I'll discuss them while in the class, but you should definitely read this to understand how job submission works on the cluster. Okay. There's a page on job submission in detail. I'm not sure what, well, there's nothing here. Okay. There's a page on trainings. Well, this basically has my videos over the last few years. So one's in 2021, one's on 2023. But this was actually the same course we have this semester. So our videos go on the HPC website, so you can look at our videos every time things get changed. So the latest one will be the most useful. So do have a look at this as well. There's some on parallelization, and then well, this I think page does not work anymore. This was once upon a time in the old cluster room. We had some IoT systems being set up during COVID times because people were not available. So we had some real time sensors. We had some sensors installed with Raspberry Pis, so people could see what's the status of the cluster. The temperature at different places was available through some nice dashboarding, but that's I think dismantled now. Anyways, any questions till now? Right, I didn't talk about file systems. So we have two file systems. Actually, this should be there on the home page. Right, so it has it in the notices. Usually, yeah. So file system details are available in the new account and login page. So it talks about how to log into the cluster. So once you get an account, you'll want to log in. So we'll discuss that in today's demo. But we do want to talk about the two file systems available. So when you want to store something, you'll have two options. One is home, the other is called WD. WD stands for working directory. That's very typical to any cluster, a home and WD. And there's a data also, that's a third one, but we only have two, home and WD. So home is much faster than WD, but the space available is only 10 gigabytes. That's the hard limit. Soft limit is 8 gigabytes. So when you cross 8 gigabytes, you'll get a warning, and after 10 gigabytes, you won't be able to access your data and add anything more to it. So you should get a red flag once it crosses 8 gigabytes. Okay, so this is much smaller in size because it's much expensive in terms of cost, and it's much faster. You can always check the quota with the quota command and so on. Right. So what is it used for? You use it for putting some scripts, like you have some Python scripts, which is only text based stuff. So you keep them on the home. Home is usually backed up. Some one or more backups are available, but you should never rely on that. Always keep a copy of everything that it's important for you. I keep my policy is 4 copies minimum. Okay, so one hard drive in my office, one at my home, one on some Dropbox. and one is available on a computer. So that way is what are the chances that a Dropbox server in US will catch fire, as well as my office, as well as my home, and as well as everything else. If that happens, then I am doomed. But otherwise, the point is that you don't want to write those scripts again, and it does not take much. In fact, when you get used to these things, you can set up write scripts that automatically back things up, so you don't even have to do it manually, right? So it's worth it, because if your job is all, if your work involves revolves around writing programs, then what's the difficulty in just backing it up multiple times, right? So you should bash scripts you can easily write to do an rsync for some data. Anyway, so you learn more about it when you start doing these things in research and so on. The next is WD for working directory. For this you have a limit of 2 terabytes, and this is typically used for storing data. So when you are running codes which generate data files which contain information about some fluid flow or something else, so that these are typically, you know, huge data files. So for that you will keep them in WD and use that, and then they can talk to each other definitely. So we have a distributed file system, in the sense that if you copy files into a folder, they are not necessarily kept in one hard drive. So we have different hard drives in the cluster installed at different compute nodes, and but it will look to you, it will appear as one folder, but the files may be kept at different places on different computers. But that is not your worry. That is typically done to make things more efficient in terms of storage and so on, and data transfer. So there are different sort of solutions available for data storage, but the point is that the same file systems, as the last line says, are mounted on both CPU and GPU clusters. So when you log into CPU cluster, you see some files. The same files are also seen on GPU cluster. Okay, because the file system are the same. You just mount them on 2 different machines. So if you delete something on CPU cluster, that also gets deleted on GPU cluster. Okay, that's sometimes there's a confusion when you start using clusters. So they're not different computers, they're just 2 different environments you see to communicate with certain other compute nodes. Right, so let's move on. Now, what are the typical applications the cluster is used for? Engineering, definitely. So fluid flow applications, heat transfer applications, we have software like OpenFOAM, Fluidity, ANSYS Fluent. So first 2, for example, are open source softwares, and the last one is a commercial software. Commercial softwares will require license. So the way it works is that there is an institute server that has a license server which has licenses for all the softwares which require licenses, for example SolidWorks, ANSYS and so on. So you will have to set up an environment on the HPC cluster that can connect to the license server to access license. So these things are sometimes these details are given in the manual of the commercial software. Sometimes you have to talk to experts, sometimes you have to try things yourself, but there is an option to communicate with the license server to get licenses. Solid mechanics, deep learning, so many Python modules are available, or you can install yourself using virtual environments. Physics, again physics community is a large user base, particularly in molecular dynamics applications. In fact, we will do a short exercise if time permits on molecular dynamics in our course, but there is a dedicated course in molecular dynamics at IIT Mandi where they write programs, and I assume they also use the cluster for that. There is a chemistry group that uses computational chemistry, particularly GROMACS software on the cluster. Then gene sequencing biology also is very popular and so on. And then there are many applications I don't even know, but many people are using that. So I'm sure if we have others who may be using different software, that I'll be happy to include that, but do let me know, so I'll include that in the next year. So what do we have in terms of infrastructure? So we have, well, this information is as of last year January. We have around 3,000 processing cores, 300 plus users. Well, I'm sure that that's many more now. We have a total of 169. We had a total of 169 nodes. So around 170 physical nodes available on the cluster. It's based on Intel Xeon processors. They are processors which are heavy duty processors with multiple cores, and they are designed to run for a longer duration without any maintenance requirements. It had a total of 12 terabytes of RAM, the memory, and it had a total of around 1000 so 1 petabytes of storage. Okay. So we're talking about a good cluster, but in terms of comparisons with the typical supercomputers or even our supercomputers, this is nothing, but still it allows people who want to start doing computational research to get them started. For people who want parallelization up to, let's say, 24 cores in total. It has 33 NVIDIA GPUs. I'm sure there are many more now because GPU based applications are growing. And as I said, it has a maximum of 10 gigabits per second Ethernet connectivity. Okay. Faster connectivity is much more expensive, and you have to have dedicated cards installed in the compute nodes to use them, so it becomes extremely expensive, so we never install that. It has a dedicated cooling system. In fact, our cluster has a state of the art cooling system, which cools the cluster. It's actually housed in a glass. Has anyone seen our cluster, the new one, the new setup? So it has a cooling system that has a cold aisle and a hot aisle, and it's basically encased in a glass box, and so that you don't waste cooling resources on cooling the whole room. So it extracts hot air which is coming from the back side of all the computers and of all the racks, and then it throws. So basically a cooling system also looks like a rack. So it has a nice fluid mechanics that works in that. So we'll have a chance to have a look at it in the future. Right, so scheduling, that's very important, because whenever you want to run something, you have to send that job to a scheduler. So as the name suggests, the job of a scheduler is to schedule jobs depending on some priority. If there is no priority, then it basically is first come first serve, and that is what we follow. There's a first come first serve policy. It may have been modified, but we definitely have no charging as of now. So some clusters have a charging mechanism. So you can decide which queue you want to send to. If you send to a queue that has some charges involved, then those charges will be deducted from your, because you have a user ID. It will, depending on how much you have available, it will get deducted from your quota, and then you have to prepay or whatever you dealing mechanism you have in terms of payment, and then those queues are much faster. Your jobs quickly goes into execution, but we don't have that. So it's basically first come first serve, because our cluster is for research based requirements, and not the supercomputer, for example, has this option available, the Param Himalaya supercomputer. So there you can get priority access if you have some money available with you. So what you do is you submit a job through a scheduler. In our case, it's called PBS, okay, a portable batch system. The company is called Torque. So PBS is a framework that's available from different companies. So Torque PBS is what we have, and there's also one which is PBS Pro, I think. But anyways, ours is Torque PBS. So most of the PBS commands are similar, but some of them may be different, and they particularly will be for Torque PBS. So it's worth reading the manual of the scheduler if you want to do some advanced things in with the scheduler. Okay, so scheduler takes care of when to send whose job to which compute node. So it has to decide. It cannot keep sending something on one compute node, because that compute node will get really hot, and it will start breaking down. So it's the scheduler's job to decide all these things. You don't have to worry as a user about these things in the beginning. If you become an advanced user, you may have to, and it also takes care of excessive usage. So in case you keep sending thousands of jobs every day, and then at some stage it will realize that this user is using too much. So your priority of each job will get reduced. So that way is it's a fair usage, that policy that is that's been implemented through a scheduler. So what does a scheduler do? So what you do as a user is you write a PBS script. It's like a bash script, but we call it a PBS script. So, in the script you have to specify how many cores you want to use for your execution, for the code execution, how much memory you need, which queue you want to send it to, and then you write a code. So, all the resource requirements as well as your code that you want to run, you have to specify in a script. You can have other executables in the same folder that the script will refer to, but this script has to be sent to the scheduler, which is also installed on the head node for us. And then once you send this command, it will go to the scheduler, then scheduler decides which node. For example, in this case, let us say N1 is the one that was given to you. So, then the job will start running on the compute node, and once the scheduler will book it for X number of hours, depending on what is the maximum available or what you requested. So, if you requested, let us say 10 minutes, and that is what we will do for exercises today. If you request a smaller time, it will typically it will get sent very quickly. If you require it for, let us say 24 hours, it may schedule it on a lower priority. So, that ways your job gets sent to the compute node, and then it will run there, and once the results are created, they will get copied back to the not the head node, but they will get copied to the file system. Depending on when it clears the buffer, they may get copied every few minutes and so on. So, once the job is complete, then the data will be available in a folder in the file system, and then you can copy that back to your local machine and analyze the data and so on. So, typically cluster is for computations, it is not for visualization. So, you should not be using the cluster for plotting data. Okay, you should be using it for computation. Then once you generate the data, you copy it back to your local machine and then do whatever you want to do with it. So, this is some sort of a mechanism of how the scheduler works on the cluster. Right. So, let us start with the hands on. So, for today's discussion, since I want to only use the cluster, I do not want to do much otherwise, I will not be using virtual machine for my local usage. You can use it if you want, or we also have Linux available on the machine in case if you have just logged into the Linux machine, whatever. I mean, by now you may have realized that it is your choice, whatever you want to use. So, for today I will be using Windows, I will not be logging to the virtual machine just to keep things a bit faster. Right. So, this is a Windows command prompt. In fact, I have installed Linux in Windows through something called WSL. So, okay. So, this is actually Ubuntu running is much faster than virtual machine. So, what we will do first is we will log into the cluster. So, that is the first thing. So, let us log in. So, typically what we do first is we ping it to check if it is communicating back. So, 10.8.1.19. So, we are getting reply back. So, that means it is available for us. SSH, my user ID, which is B Gaurav here, 10.8.1.19. And by the way, how many people have not got an HPC login as of now? Oh, quite a few. Only how many have got a login? Okay. So, you just have to then follow with me, or if you are friends with someone and you are happy to share your login details with someone. Usually I do not recommend that, but for today's I mean that's purely up to you. Okay. I was hoping, so, how long is it taking for getting login these days? So, the first thing you do is you say SSH. SSH is a secure shell for connecting to the cluster securely, right. So, once you do that, it will ask you for a password, or it may not ask for a password if you have already set up a passwordless login that I will talk in a few slides from now. It is the same approach that you have used for Git. We have generated a key and a lock pair and then a public key and a private keys, and I have shared the public key on the cluster. So I'll discuss more in terms of that, but if you have not set it up, then you will be prompted for a password that you have to, yeah, that password is your HPC password that you got when you got the account created. All right. So this is how you log into the cluster. Let's look at the directory structure. So if you do an ls, let's do a pwd first. So this is my home. So this is /home/b Gaurav. In fact, I can go up, then I am in home, I can do an ls here, then I can see all the users of the cluster. Okay. So this is my way of spying and figuring out how many users are on the cluster. But this is okay. I mean, see, cluster, it's a Linux based cluster. So whatever you don't have access to, you cannot use. If you try to CD into somebody else's account, you will not be allowed unless they have mistakenly or genuinely they have allowed others to use it. By default, it's only available to those who have access to it. Okay. So I'll go back to my ID. Sorry. Right. So this is my home. So in my home, I have some stuff available that I have kept, I have stored. You also see that there is a WD available here. So if I do an ls -l, full screen. So you see that WD actually refers to, it's a link. It's a link to WD/WD/users. So this is a different file system. So right now we are in /home/b Gaurav. This one is /WD/users and then followed by the ID. So if I do a cd/wd, I am actually doing a cd to this folder. So if I do a pwd now, I am in, well, actually it shows wd, but actually I am in /wd/users/b Gaurav. Okay, so this is my other file system. So I have some more files stored here, which are much bigger in size of a few gigabytes or terabytes. Okay, so all my Singularity images, which are of the size of a few gigabytes each, all my data files and so on, I keep on the WD. Right. So let's get started now. Now that you have seen all these things, so the first thing we'll do is we will prepare a virtual environment so that we can install some packages through pip and then use Python as to our convenience. So what we'll do is do a Python followed by -- version. It's a Python 2. It's quite an old version of Python. I want Python 3. So for that, if you do an SCL, which is SCL stands for Software Collection Utility, which allows you to provide different software or different versions of different software to the user depending on what they want. So if I do an SCL -- list, in fact, there is only one software available called Python, RH for Red Hat, but that's okay. So it's a Python 3.6 that's available in all compute nodes. So what I can do is I can enable that. So I can say SCL enable, and then a tab should complete it, and then I'll say bash. So bash is just because I am using a bash shell, so it will enable this environment on bash. So now if I do Python -- version, so this is 3.6 now. Okay. So all these commands are actually there on another slide. So you will have access to all these commands. You don't need to remember them or write them right now. So let's just follow with me as to what I'm doing here. Any questions? So now that the Python is the version that we want is available, now I will install virtual environment. So first what you will do is you will have to upgrade pip, because pip may be of an older version. So what we do here is I'll say, I think it's pip 3 here. Yeah, so let's say which, right, so pip 3 is available, so we'll use pip 3. Okay, sometimes there's a confusion between pip and pip 3. So let's use pip 3 because we're using Python 3. So pip 3 install, and then see, this is a cluster. So, we are not administrators here. So, whatever you install has to be installed with -- user, so that whatever gets installed on your home directory. It may want to install something in root which you may not be allowed. You do not have sudo access to the cluster. So, always do pip install with -- user, and then I will do a -- upgrade because I want to upgrade pip. So, I will say pip, but this won't work because we have to use proxy. Proxy is still used on the cluster. So, for that I will have to say proxy, and those who are how many people have been here for more than 1 year at IIT Mandi? So, you know what a proxy is, right, because you were using it earlier. For those who have joined recently may never have heard about proxy. So, what you have to simply say is proxy, and then it's a proxy server, http://10.8.0.1:8080, right, and then you press enter, it will upgrade pip. But for me, I do not want that because I already have done it. So, I do not want to waste time on this. So, but available for you to next we will install a virtual environment. So, I have a folder where I install environments, that is called virtual envs. Okay, so let me install it there. So, I have a few that I use for testing. So, I go into this folder, then I say Python, right. So, I will say Python 3 -m, the same way we did it in the virtual machines, and then we will say venv, and then we can name it anything we want. So, let us say venv class. Let us put a date here, that is much better. So, venv 14 Feb. So, this will set up a virtual environment for us. If I do an ls -l, you can see that venv 14 Feb is available now. The same way, and you will activate now, activate this now the same way you have done it in the past. So, you simply say source, virtual environment has been activated on the cluster. So, now I can do a pip list. So, it's there's some issue here, but I think it's just taking some more time for something else. There's only 2 packages installed, pip and setup tools. So, what I can do is I can say pip, pip 3. Let us try pip 3 list, same issue. Okay, so let us say pip 3 install, and then you just install whatever you want. So, let us say numpy. So, now it will collect numpy and install it, but again it will not work because we want to set up a proxy here. So, I will have to say pip 3 installed, and then -- proxy equals so now it is working. So, you see that it is already installed numpy now. So, now if I do a pip 3 list, numpy can be seen. Okay. Any questions till now? As I said, I will share the slides once I am done with this first part of the session today on Moodle, so that you can start trying these commands by yourself. So, this is the head node we are on, right. N199 is actually the address for the head node, and the compute nodes will be N1, N2. So, you can actually do a ping N1. Ping well, we can simply do SSH N1 or N10, let us say. So, SSH N10 is to connect to N10. Let us do N31. So, it has taken me to N31. Usually you should not be doing this, you should not be logging to the compute node yourself, but that option is available in case sometimes what happens is you are running a job where for some reason the job got killed, there was a power outage or something, and your data files are available on the, they could not be copied back from the compute node to the file system. So you can manually go there and copy things, and you can see what all codes are running also. So here right now nobody is using this. So top is a command which is used to check. In fact, somebody is logged in. Anyways, so I can do an exit and come back out to N199. So let's go to a folder where I have some interesting things available. So I have a folder called home. So there is a folder called demo me522. We'll go to the Python folder where I have a Python script. Let me clean this and first. Let's clear it. You don't need to worry about these things. So if I have a certain number of files. What I'm interested right now is in python_script.py. So let's have a look at this. Now you see that GUI is not available as of now, so I can only see things in the terminal. So this is where using the terminal or learning how to use it effectively is useful. So this is a Python script. It imports NumPy first, and then this is a comment. Then I have set the value of two variables a and b. Then I print a, b and a plus b. It's an f string, so it evaluates whatever is inside the curly. And it also prints np.py just to check if numpy is being accessed, and then these are all three comments, and that's it. So basically it's a code that adds two numbers, prints them, and also prints the value of pi. That's pretty much it. Now what I am doing now is I am going to run this code on the head node, which is something you should not be doing. You should not be running anything on the head node. Now this is a very small script just to test something, which is fine. But if you are running a compute job, then you should be sending it through the scheduler. So Python followed by this Python script, so it runs. So I am happy that things are set up properly. Now if I had, for example, if I deactivate this virtual environment, and now if I try to run it, it will not run. It says NumPy not found, because NumPy is only available in the virtual environment that I am available, that I have set recently. Okay, so it's always good to check a very quick example just to make sure things are working, because you may send a job without testing it, and it may reach the queue after 5 days and then it crashes. So there is no point in that. So it's always good to try out some test cases, very small, very short, very quick test cases, to make sure all the environments you need, all the setup you need, all the framework you need is working fine. Then you should run a bigger job. Should we discuss the PBS script? Let's do that. Okay? We started a bit late because I don't want to break up before I discuss the script, so that you can actually try something by yourself. So what we've done is we have set up the environment and we have installed packages using pip. So now what we'll do is we'll talk about PBS script. That is a script that we have to write to send the job to the compute nodes. So let's discuss that. I'll clear things, do an ls -l. I already have written a script just to save some time, but you can always copy it from the website of HPC, and then you will see that it's very similar to the standard script we have available there. So let's open it. I'll use Vim for editing this _PBS. And by the way, I'll share this. This is not very legible, so let's use nano if that works. Can the people at the back read the text? Now? Okay. Right, so let's try to understand the script. Let's ignore these first. Let's look at the actual code that we have here. So what we are doing first is we are doing a cd as a change directory to some environment variable, so which is like the present directory that we are in. Okay, so there's nothing interesting here. And then we echo something. Echo is for printing something on the terminal. That's called standard output. So we say just running on, and then we are doing a cat. So cat is to print the contents of a file, and this environment variable called PBS underscore node file contains the information about the file that has information about the compute node. So your job will get sent to a compute node, but you do not know where it's going to get sent. So using this environment variable PBS node file, which points to a file which has information about the compute node that the job is being sent to. So I can use this cat command to print the value of the address. It will be N31, for example. So I know that my job got sent to N31. If anything happens, I can track it back from N31. Then next is well, this is for printing this on the screen on the terminal, and the next one is actually sending it to a file called machines.list. I just named it as machines.list. It could be anything. It could be machines.txt. So that this file will get created, which will have the information about the compute node the job got sent to. Now I will just echo something on the terminal. Program output begins. The first thing we will do is now we will source the virtual environment. We will try without using this environment and see that it does not work, and then we will simply run the python underscore script.py. Okay, is that clear? So we are basically running this Python script with some extra information just to aid in our understanding of where the job got sent to. Let's look at these lines which have hash PBS. Okay, a hash is usually for comments. So if you send this as a normal bash script, if you run it as a normal bash script, it will all get ignored. But if you send this to the scheduler, the PBS scheduler that we have, they will be able to understand these commands. So these are called directives. Okay, directives are, you are giving some directions to someone to understand something. So once we send this script to a PBS scheduler, then they will be able to understand what this means. So let's understand different options. So we have a -q following hash PBS. So this stands for the queue. So I am sending this to a private queue called priv SE. So SE stands for School of Engineering. So earlier we had a School of Engineering that included people from mechanical, civil. So now we have split, but the queue is still there because the money came from the School of Engineering. So everybody who was a part of School of Engineering has access to this queue. I am using this because it's a bit faster than open queues like day and week. Next is -o. And by the way, all these things are also explained on the website of IIT Mandi, and or you can just refer to Google. Most of the clusters are PBS based. Well, they were PBS based earlier. Now it's Slurm based. We'll talk about Slurm as well, which is the scheduler that is installed on Param Himalaya. But today we'll talk about PBS. So these commands can be found out through manuals, internet, and so on. So -o is for output file. So there is no standard output here. When you run something on terminal, you get the output on terminal. But since you are sending it through the scheduler to a compute node, there is no standard output. So everything that is supposed to be printed on the terminal will go into a file called out.o. You can change the name here. So I have set it to out.o. In fact, I have set the name out.o. You can have any name you want. Then if there is any error, that goes to a file called out.e. Okay, so the error and output they are channelized differently. Because this will help me if there is anything in out.e at any stage, I can figure out that there is an error going on somewhere. This is the name of the job, just for your convenience. If I am running a parametric study, I am running a simulation for 100 particles, 1000 particles, 10,000 particles, and so on. So I can have a nice name saying that sim 1 underscore 100, sim 1 underscore 1000, and so on. So that will help me understand which job is which. This is this -l is very important. This is for understanding what resources you want. This is for telling the scheduler what resources you want. So I want one node. So one node is that one machine that you have, and one core. So processes per node is basically one core. So this is a serial job. It's not even a parallel job, but this is for demo. So later when we learn about once we write parallelized Fortran codes, then we will be able to use this, we will be able to change this to 2, 5, 6 up to 24. If you put any nodes equal to 2, then you take 2 nodes, but then what happens is that the nodes have to communicate with each other, and remember that communication is at max 10G, and 10G communication for a code execution is very slow because you may be sending data. So this is through something called MPI, message passing interface, that we will talk about in this course, but unfortunately our cluster does not allow inter-node jobs. Well, it allows, but it's actually much slower than what you would get if you just run it on a lesser number of processors. Okay. So you will want to keep this nodes equal to 1, and then you can increase this ppn value up to 24. So for today we will keep it 1. Wall time is how much time you want to reserve. So I am taking only 2 minutes here because I just want to demo something to you, and minus v is for copying environment variables. We will talk about it in the second half. So let us run it. Let us do a control X exit. So the way you run this is using the qsub command. So let us do that. Qsub followed by this, you press enter. So once you do that, it gives you an ID. So this is the job ID that is allotted to your job. Now to check the status of the job, there is a command called qstat. So this tells me that it's this job ID dot n199 and so on, the name of the job, which user is running. Sometimes as an admin, if I run it, I can see all the users. Then time and the status, C stands for completed. So it's already completed because it's a simple Python code, and the queue it went to. Okay. So let's do an ls minus l now. So now we can see that the out.e is empty, out.o is what was generated at 14 February at 1807. I think the clock is slightly offset. So I can actually do a cat o running on, then it prints n31 because n31 is one of the nodes available to private SEQ, School of Engineering. Program output begins, it prints the value of a, b and the sum, prints the value of pi, and that is pretty much it. Let us also look at machines.list. So I do a cat machines.list, and that has the information about the compute node that the job went to. So I will share this script on the, I will push it during the break to the repository so that you can download and try it out yourself. For that you will have to copy this. The easiest thing to do is just copy paste. It's much easier to start with. Later I will talk about how to copy files from into cluster to your local machine. Any questions? Now many of you may not be able to try things, so in that case you just have to, I don't know, right. Let us do one thing. Let me disable the virtual environment and then see if it works. So let us comment this out, okay, hash for comment. So now what is happening is I am not sourcing the virtual environment. Now this virtual environment is getting sourced on the compute node, not on the head node, right. So this command is, even if you have enabled the virtual environment on the head node, that has no meaning because this job is getting sent to a compute node. So the environment has to be enabled there. So let us save it, and now I will run it again using qsub. Let me clean these files. So I have a sh that simply deletes the files which I do not need. It is much easier to, rather than deleting files manually every time. So I can run it using bash clean.sh. So now you see that those output files and machines.list has been deleted. So I will do a PBS python.sh. It's a different ID this time. Let's do a qstat. So this one is 652. Okay, so my job was next to the earlier job I sent. So it's been completed in 0 seconds. That's much lesser than 1 second. And let's do an ls. So this time you see that out.e has something in it. because there was an error. So, let us check the error. Not found because I have disabled the virtual environment, so numpy could not be found. Okay, so this is a way to test things and making sure that your job will, so even though it may be working correctly on the head node, environments have to be enabled correctly on the compute node. Right, so let us take a break for 5 minutes and then we will start again. I will give you some time, 5 minutes for people to practice or at least look at the things that we have discussed till now, and then since many of you do not even have an account, so I will start with the demo again and then you can look at the video later and try things yourself, but do try these later. Okay. So break for 5 minutes.